Hello guys, welcome. So in this video we will gonna go talking about diffusion models, the basic foundation of diffusion model, which is the forward and reverse diffusion processes. So in the previous video we go through the application and the overall landscape of the diffusion models. We see how diffusion models landscape look like in our overviews, and so in just a brief overview of that, and we see the architecture and application and the use cases and the different application, like in different modality of how diffusion models has actually impacted the every field within AI and all the sciences and all the domain in the real world. So, and for that, we will start from the to understand the diffusion better. So, I will just understand. I will just tell you some of the processes that happen in the diffusion. So, we will not directly go into the paper. So, we will just understand these fundamental concepts in depth. And this is the forward diffusion processes and reverse diffusion processes in depth, and we will just upgrade our knowledge to move forward. So, like we will go into the in the upcoming video. We'll go to classifier guidance and other higher level topics. So for that we need to understand this topic so clearly. So rather than going to the paper, so I will explain all the maths what's involved here. So and you can directly grasp more easily than going to the papers and just saying this you. So in the forward processes, actually you can, so I will show this. So in the forward processes, you have a image which looks pretty good, which is noise free, and what the goal is from this noise free, go to complete noise. So go to complete noise, and this is from noise free to complete noise. So the reverse diffusion process is going from the structured data, which have structure and the full signals. So strong signals of the distributions which it belongs. So it has the strong signals of distributions, and when from the pure looking images we go back to this pure noises. This is the process. This is the forward diffusion process. For that, we iteratively add noise. So from we will, for example, we have this guy image. So imagine like this guy image and this guy image, and this is, so we'll go up to this. So consider the time step as hundreds. For our consider the time step as thousands. So from here to complete noise here, from this is the real looking, and this is the this image. So from here, from the pure noise, from the pure real looking man to pure, this is xt and this is x0. So from x0 to xt, what we do is this is the forward processes. What are the operations actually happening here? So and and what operation leads to this pure looking images to the complete noise or complete, which is like absolutely which have no signals of the actual data x0. So and so what are the operation actually happening here in the forward diffusion processes? So the the operation what is happening is actually we adding noise. So in the forward processes we add noise to the data step by step. So and the and beta t. So we'll introduce another thing. Is beta. This beta actually is something we have to. So I want to tell you that is, and this tell how much amount of noise added. So amount of noise added. So this beta t. So I will introduce this term beta t. This is the amount of noise added from year to year, year to year, year to year. So from one step to two step, how many is how many amount of noise we added. This t, the subscript t is which time step. So at how at what time step we add how many amount of noise. This beta two will give this. So and the beta t is actually from here beta t from going from x0 to x1, this is the beta 1, and from going x1 to x2, it's x1 to x2, this is beta 2, and beta 3. As we go forward, this become beta t. So guys, so this value actually like this in this order. So what actually it means, we increases the amount of noise as we move forward. So we'll also see the implementation, code implementation, and as we approaches to the final, we start adding more noise than the initial time step. So we will continuously this beta. So if you see the graph of beta and this time step versus beta value, this will be linear. So this is the beta value, so beta, and this is the time step, guys. This is the beta and time step. So as time step increases, this will grow linearly. So it means that the amount of noise will be more when our time step become high. So this is the linear this beta value goes linearly, which actually means that we will from at small time step we add less noise as beta approaches to the time step approaches to a higher, so our beta value will go higher and we will add more noise. And and to get any of these images, so this is suppose this is xt and this is xt minus 1, this is xt. So we want to go from this xt minus 1, we want to get xt given xt minus 1. So how can you go from here to here? So for that we will introduce one thing which is q. So this is q. So given x given xt minus 1, we want to go to xt, which actually means give me less noisy. So I will predict more noisy image if you keep less noisy image. So we are telling predict this more noisy image given this, and this will actually have this form, this Gaussian form, because we are adding Gaussian noise, and this will take the Gaussian form, and which will actually be xt and and two parameters, which is the mean 1 minus beta. So 1 minus beta t x minus t and beta t of I. So this will be the sampling procedures. And so for the product, so given this I want this given this. So which actually means that I will. So we are just telling the model, listen, just give this. No, not a model. This is, and I want to tell the forward processes is not learned actually. So it's a highly trivial task actually, isn't it? So it does not need model. We just add noise by our fixed functions, which is this linear schedule, which just add noise, and rather than it's nothing to learn, and just we add from the predefined schedule, we make this like this type of schedule. So linear schedule, and this will add noise at linearly, and there's nothing to learn. And what happening here is so here so what we're doing is given this image, so it has some pixel value. So this we are doing operation in the pixel value. So I will just if this is an image, so if it has value between some values, so suppose it has value between -1 and 1, so we it's converted to this range, and what we're doing is just multiplying this by this numbers, which will be look like something 0.5 and 0.4 and like this, and we're multiplying this. So and we are just shrinking the mean towards zeros, so we are shrinking the values between just zero mean of the distribution at zero, and we are making this beta closer to 1. So beta, we want to make this just closer to 1. So as time step increases, so first time step we have 0.4, and so imagine this is 0.4, 0.5. So when the t increases, the value will this value will approximate to 0, and this mean will be 0, and the beta t will be 1. So as time step increases, it will approach towards 1. So you can see the sequential order. So and this variance will approximate to 1. So and this will convert to our prior, which is a Gaussian distribution. So it will approximate to our prior distributions, and our image distribution will just convert into this Gaussian distributions, which have zero mean and unit variance. So this is the goal of the forward processes. So guys, I want to just give you some. So we find Q up. So I like wait, so we find actually we can find this q of x t given x t minus 1, but we have to reach x t minus 1 to get this x t. So it will be very efficient if we find this. So if you can find this, it will be very efficient for us. So how can you find this? So it has a closed form solution. So it will actually be a Gaussian, and I will tell why this is Gaussian. And this is alpha t bar of x0, um, so 1 minus alpha t of I. So so why this has this reverse process, this processes have the why we are just giving this given the x0 when we are just taking this Gaussian form. So because because beta the value of betas are small, so the both processes, so the forward processes and the backward processes have the same functional form. So if beta t is small, then it will approximate to and this will we can just give beta t is small, so we can take the same functional form as the forwards. Forward because we are adding Gaussian noise, so we're using the Gaussian functional form while in the forward. So and if beta t is smaller, we will for the they have also same functional form. The backward will also have same functional form if the beta t is small enough. And guys, let's do summary. how this let's derive this equation. So for the derivation of it, I will going to give you this overview. What this alpha t is. Alpha t is 1 minus beta t. And what is this alpha bar t? Alpha bar t is the cumulative product of the alpha bar. This is the product of from I1 to t. So from I1 to t, and this is alpha. You can just write s is equal to 1 to t. So and this is the what we need, and let's derive this equations from the scratch. So we have x1. So we have x1, which is in this form we have already discussed. X0, because this is 1 minus beta t, so this will be x0 plus root over of 1 minus alpha 1 dot this, why this is alpha 1. So this is 1 minus alpha 1, and for the first x1 image, this will have this form. So and for t is equal to 1, this is, and for t is equal to 2, we will have x2 is equal to alpha 1. This is alpha 1. So this is alpha 1 and this is alpha 2, and this is x1 plus 1 minus alpha 2 and epsilon 2. And then if you substitute this quantity here in this x1, so this is x0, so this will be, so this is x1. So if you substitute this in x2, x1, substitute this whole quantity here in x1, so substitute this here, it will take the form. So I will write again. So which will be in turn alpha 2 of this whole uh this whole thing here. So which actually have this form, alpha 1 x0 plus this term here 1 minus alpha 1 and epsilon 1, and this is the whole thing here, and plus the other thing what's remain here. So I'll write this alpha 2 given, not given, so just alpha 1 minus alpha 2 product epsilon 2. So you have x given x0. So for x2 we just write this, take this value of x1 and just plug it here, and this is the same thing x2. And if you go like this below and below, like if you substitute in x3 if you substitute if you substitute the x2 root over of alpha 3 and x2 dot f not epsilon, but just if you just substitute this quantity here plus 1 minus alpha 3 into epsilon 3, and if you substitute x2 this quantity here, this will take this form like this, x3 will take this form like this. So 5 till I'll write it so for that last time. So nil alpha 3 alpha 2 alpha 1 dot x0, so you'll get the understanding much more better. So and alpha 3 alpha 2 1 minus alpha 1, and this epsilon 1 epsilon, this is epsilon So plus we have storm alpha 3 1 minus alpha 2 epsilon 2 plus this epsilon. So and this is 1 minus alpha 3 and this epsilon 3. So this is x3. I know, and we want to. This is given x0, so we find given x0, we find x3. So for arbitrary time step t, what you can do? So let's right now we are finding x3 given x0, but we want to find xt given x0, which is our mission right now. So for that, this xt will be actually this will be the cumulative product of these alphas from alpha 1 to alpha 2 to alpha 3 to, and so on, and x0 plus this is the summation of s1 to t. And what is this? 1 minus alpha s. So I'm just dot epsilon s. So this is our first part. So this is our first part here, and the other part is this thing. So this thing. So we are just this is like this. You can just analyze it from here. So this our part is here, and this part is here. So and from here we will go forward. This part will here. This other part. So just we are just converting into summation for the t type for t step. So and from s1 to t we are moving, and it is also Gaussian distributed, and we can actually express this xt as it's xt as this which has been from some which is sampled from Gaussians of having this mean this alpha t bar given x0 and this alpha t square that I is the mean a mean of the distribution and the variance of the distribution. So we have to work on the variance part. So let's work on the variance part. So let's derive this part, this epsilon. So this will be actually this is the variance of the distribution. So we're going to derive this thing. So this is actually will be the variance of from s1 to t and root over of 1 minus alpha s epsilon s. So since here epsilon s actually are the independent and identically distributed Gaussian variables, and this has a variance one, and right now we have the variance of the sum. We have the variance of the sum, and this can be written as the sum of the variance. So it can be written as the sum of the variances. So from s1 to t 1 minus alpha s. So this will be 1 and it's epsilon s, and we can write the sum of the variance as we can write as the sum of the variances. So rather than the variance of the sum, and this epsilon t here, epsilon t, this is actually will become 1 minus alpha t bar. So and So we arrive right now to this equation. So and let's plug it into back. So q of xt given x0 will be, we find this variance like this, and we already find the mean. So n of xt is equal to root over of alpha t. We already find this alpha t of x0 and 1 minus alpha t into I. This is the identity matrix, and this is the closed form solutions of the Farad processes. We can just randomly take some arbitrary time step t and get get the image at that time step and observe this. So let's implement it into the code part. So I'm just importing some of these, just doing pip install what thing we are in TensorFlow test and TensorFlow add-ins and ENI ops. EIN ops. So we will just initializing it for our purpose, and I'm just importing some of the basic libraries here. Just NumPy, Plotly, Matplotlib, GQDMF, Python Imaging Library, we're importing image and TensorFlow, Keras, and model sequential from the Keras layers, and importing layer from Keras layers, and importing Anon from Keras layers, TensorFlow Keras layer, and datasets as TFDS, and rearrange just importing from this. From here, I'm importing this rearrange and as sorry, I'm just ignoring some of the warnings given by the colab, and then what I'm doing here is just configuration of the GPUs. GPU option config. I'm just setting up here. So and so let us set a parameter up for the data set. So we will gonna go use 42 by 42 images, which has one channel. So this will be black and white image, and we're defining a basket as 64, and this function we are creating, which will just take this tensor x and just change into the float 32 bit tensor values, and just converting the values. This will actually help. So I have also write the, so let's use it. So I have also used some of the defined steps also. So let's see here. So if I can show you. So this is the pre-forces. So here, so it's the same normalization helper. So which will just takes this x and convert into float 32, and just it's just doing what it's doing. It's just dividing by this. So if you have the images values between 0 to 56, you are just converting the values between 0 to 1. So this is the operation you are doing, and this load the data. So loading the data from this TFDApp module. This is TensorFlow datasets, and from here just loading this amnest and taking out the label, and just mapping the data. So normalize. So this will what it will do. It will actually convert these values between normalized values between -1 and not 0 to 1. So it will normalize values and shuffle the values. This map the preprocess dot data dot auto tune, and what is doing here? It will doing three of the shuffle. So you can just do calculations here. So any value between 0 which it will convert to it in this range. So and shuffle this using this shuffle and convert into patches and tee up the data that auto tune. So it will preface the data when the model when we're training a model. So So if you have a GPU and it will just store the data into the CPU, and if you are processing the GPU processing, so and after that the processing happen, it will just send the data into the GPU, I think. And this will return the TF tensor while iterating. So TFDS as numpy array. So and just get resets calling it, and we will already define this, so it doesn't need. So it's the same. So I will from this cell. So this cell now, this first cell, I think, unable to connect to runtime. So it's runtime type. So let's move on this, unable to connect to runtime. Okay, so it's okay. That's fine. So we need internet actually. So what you're doing is just getting the data from here, and let's do some of these, initialize some of the calculations which we needed. So this with the number of time step for the diffusion process, for the polar diffusion process is also backward, and this is the fixed beta schedule that linearly increases from this values 0.001 to 0.02 over given time steps, and we're calculating beta using a linspace method from NumPy, and calculating the alpha as 1 minus beta. So alpha represents the fraction of the original data that remains. So it's a complementary of beta. How many fraction of the data that remains. So and this alpha bar as a cumulative product of alpha to represent the product of over time steps. So and we dot com prod of alpha with 0. So I'm printing alpha bar. Adjust alpha bar to include a starting value of 1 for the time step 0. So it will, what it actually do, just it will just add starting value as 1 for the time step 0. So and what we're doing is just concatenating it, this np dot array of which has the 1 and 1 points, and just what it's doing it, and alpha bar which is alpha bar here, and it's minus 1. So we are defining here and giving the axis as 0 and printing the alpha bar, and this what we're doing here, just computing the square root of the alpha bar and square root of 1 minus alpha bar, and this function to set random number generator and set which can be used for reproducibility, and just setting the key and just creating this function for a noise which will generate random noise with the same shape as x0. We're just giving the shape, it creates some numpy. For numpy, just we are saying create the image, create the noise image. This is also image, which has the same shape as the original x0. It will create some noise, and what we're doing, we'll apply this noise. And what we're doing, we are just calculating a reshape square root of alpha bar t. And what we're doing here is just taking this value from the square root of alpha bar at the given time step t, and reshaping it to the dimension of this given here, which is a Fourier tensor, which will help when doing our operations. So and what we're doing here is just extracting and receive the square root of 1 minus alpha bar for the given time step t, just receiving it to this dimensions. Giving time step and this value. I just it will take some values from the given for the given time steps from this array of what's this values. So it will just take some of the values from here. So it will take from this numpy array given the time step t. And compute will compute noise image by combining x0 with noise and scale by the respective square root. So what we are doing here is actually creating noisy image using this mm, receive square root of alpha bar, which is this, and multiplying with x0 and this receive noise, receive 1 minus square root of alpha t into noise, and still return the noise image and noise. And this function will actually just give some of just sample the time step, arbitrary time step. So in the diffusion process it can just pick the random time. So this function is used to, rather than speaking going sequentially, if you want to just go to the put arbitrary time step t. So for that, this generate time step is needed. So so it will just this is used for actually for this generate time step is needed when we are sampling the time step, arbitrary time step t. Uh, let's visualize what the forward diffusion do. So we have to do something here. So what we're doing is just taking. So we have already downloaded this data, so you can just so result data sets. So this is the data set. So we need, and this is the data we're using Amnest in our case. So here what you're doing actually is just what you're doing is just next iter of data set of 0. So we are taking images, just visualize out at the few steps. So we are taking the sample Amnest some images like this 9, and I'm just plotting it. So 15 comma 30, creating this figure, PLZ figure, and just going through this values of time steps. So we are just take this 599 190 this time step, and just what we're doing here is just noisy image noise. So forward noise is equal to 0, and we expand dimensions. We give this sample amnest comma 0 comma will pass also and with array of I comma. So it will just give two things, which is this forward function will give the noise image and noise given the sample amnest. Creating one subplot again here. So for the plotting of this noisy image, and we are just what are doing, we're just plotting the noisy image, and we just cmap as gray we given here, and it will give this as a 5 times step 5 and 199 and 100, and this is the time step you can see. So this are, so our image is actually going from the this real looking images, our data, the structure in the data is actually destroying by the forward diffusion processes, this forward noise function. We're just taking this image 4, which is this image, and it is just doing this, adding this function, we're just adding this noise in this fashion. So this is 99, and I can just show you the another thing. So if you can see the 50, so I have to run all these codes. So you get the less because I haven't run it, so it will give error. So Yes, so I have to run all this thing, but so if I run all this thing, run also, it will give the list my same as here. And this is it for this video, and we will look at it, the reverse processes, which is which we will learn through the neural networks.